Hello students and welcome to the lecture on the crossover operator. The 18th lecture in the lecture series for the course of Introduction to Soft Computing for the Electronics and Telecommunication Engineering students of the 7th semester, Goa College of Engineering. I am Ms. Purti Savardekar, the faculty in charge for this course. In the last lecture, we discussed and understood the rank-based selection technique. In today's lecture, we will focus our attention on the next operator, the crossover operator. Let us begin. The crossover operator is an operator that is responsible for transfer of genetic information from an individual of one generation to the next. The crossover operator works on two parent strings. It merges genetic information by picking out information from the parents and then exchanging that information using an appropriate crossover mechanism. Offsprings that are generated this way may be worse in fitness, may have the same fitness as the parents, or may have better fitness. The hope is that combining elements of genotypes with good traits should lead to offsprings that will have a better fitness. This is actually true in real life breeding of livestock. Crossover is a process that mimics biological recombination. There are many types of crossover operators published in the literature, such as single point crossover, multi-point crossover, uniform crossover, cut and splice crossover, scattered crossover, intermediate crossover, heuristic crossover, etc. The choice of a particular operator is representation dependent. What do you mean by representation? Okay. So before we go ahead and try to understand the types of crossovers, let us quickly learn what a genotype representation is. Genotype representation is one of the most important decisions to be made while implementing a genetic algorithm. To ensure a successful implementation and to avoid a poor performance, choosing an appropriate representation and properly defining the mapping between a genotype and a phenotype is extremely important. The three most commonly used representations are binary representation, real valued representation, and integer representation. Binary representation is one of the simplest and most commonly used representations in GAs. When the problem solution space consists of true or false type of variables, the choice of binary representation is natural. In such a case, a 10-bit chromosome may look like this. The next genotype representation is the real valued representation. When the problem solution space consists of continuous valued variables rather than discrete, the choice of real valued representation is natural. The preciseness of floating point numbers is limited by the computer. In such a case, a chromosome may look like this. The next genotype representation is the integer representation. In case of discrete valued variables, many a times the problem solution space is not limited to a yes or a no solution. For example, if you want to encode 4 directions, east, west, north, south, we can encode them as 0, 1, 2, 3. In such cases, integer representation is required. Then the chromosome may look like this. Now that we have understood what a genotype representation means, let us come back to the crossover operators. We have now understood that the choice of a particular crossover operator is representation dependent. The first type of crossover that we will study today is called The single point crossover. Single point crossover operates on binary and real valued chromosomes. We select any random number between 0 and n, where n is the length of the parent chromosomes. This number is the point at which crossover will occur. Hence it is called the crossover point. Now, two new chromosomes will be generated from the parent such that the genetic material to the right of the crossover point is exchanged. To understand this better, let us consider this example. Here we have two parent strings with the binary valued entries. The first parent is 1010111 and the second parent is 1111010. Let the crossover point be 3. Then we see that the offsprings are generated such that segments after the crossover point 0, 1, 2, 3, that is 111 is exchanged with 0, 1, 0. And the new individuals are 1010, 010 and 1111, 111. This is the single point crossover. Now let us consider the multi-point crossover, which is a generalization of the single point crossover. One case of multi-point crossover is the two-point crossover. In a two-point crossover, two random numbers are selected between 0 and n, where n is the length of the parent chromosomes. These are the two crossover points. Now, the genetic material between the randomly chosen points is exchanged. The genetic material between the randomly chosen points is exchanged. To understand this better, let us consider this example. Here, we have two parent strings with the binary valued entries. The first parent is 1010111 and the second parent is 1111010. Let the crossover points be 1 and 5. The genetic material in between these 2 points, that is 1011 and 1101, is exchanged. So the offsprings are 1011011 and 111010. This is the 2-point crossover. Now let us consider the scattered crossover. In a scattered crossover, we first create a random vector of binary values. The length of this vector is the same as the length of the parent chromosomes. Each element of the vector is either a 0 or a 1, binary values. Now an offspring is generated with as many entries as this vector, and the entries in this vector are checked as the offspring is getting generated. If the vector consists of a 0 in that location, the material from the first parent is taken, and if the vector consists of 1 in that location, the material from the second parent is taken. The second offspring may take on exactly the opposite parent values. To understand this better, let us consider this example. Here we have two parent strings with the binary valued entries. The first parent is 1010111 and the second parent is 11111010. Let the randomly generated vector be 01001000. Then the first offspring will have the first parent entries wherever there is a 0 and second parent's entries wherever there is a 1. Then the second child will be exactly opposite. So therefore, in our case, the first offspring becomes 1, 1, 1, 0, 1, 1, 1. And the second offspring becomes 1, 0, 1, 1, 1, 0, 1. This is the scattered crossover. These are just some examples, few examples of crossover techniques. As we have discussed before, there are many more. I hope the content that was covered in this video is clear. Let us now continue this discussion in the live Google Meet. See you there. Thank you.